Here's an example of a component simulated in NAstran finite element analysis. It's a plasticity simulation of a yoke, a ring which a belt is attached to during lifting. And the main reason for doing this is to see if the welds are going to hold. So I had to draw the welds and the attachment points. And the conclusion of this analysis is that the component is not safe for when the load is full. You can see these red areas which are at risk of failure in a way. Now the loads are applied with safety coefficients based on Eurocodes, DNV, and what other standards you would like to apply, American, European, with local coefficients, with local annex perhaps. But that's how it works technically. The load is multiplied and the strength of material is reduced, so you have double safety, and about 30% extra load was applied and about 30% of material strength was removed for this ultimate limit state. This red area is loaded with it has stresses above 360, which is the limit, and then that produces a risk of pull through, so the attachment might get disconnected by causing this area to fail and just sliding out once it opens up. This area then also is at some risk of failure because there's a full area being loaded at near the extremes, but in the simulation that's holding, so that might actually hold the design load, and so forth. So the interesting thing about this simulation type is that you can see the elastic part continues until approximately here where the first red one shows up. That's the plastic yielding inducing, and so technically without any permanent deformations it will hold about half the load, and that could be cyclic loading safe as well, and the welds are completely safe and everything is fine. But then you increase the load, suddenly these high stress areas get relaxed in the formation, allowing the stresses to redistribute, and then the thing yields, creating a large area of plastic, which means continuous deformation area. And when you reduce the load, the residual stresses are staying behind, so once the load is removed, the plastic deformations, they have an uneven stress area left behind, which could make the component sensitive to a different loading direction, because these residual stresses will sum up with the next loading cycle in case it's somehow different. And we can see tiny, very tiny amounts of residual stresses in the welded connection, which seems to be okay. But another way to see this is with these ISO curves, and you can see that in this large load, this area is just basically holding on for its survival at stress levels that are relatively high. S355 steel, once multiplied by a coefficient, is 320-ish, and this area has some stresses within that range, while the top one is just pretty much completely on the edge, pull through. This load distribution depends on the type of connection. If it has a big cylinder, that might reduce the bending moment but probably increase the tension, so that should be simulated. And Yeah, so this is a pretty interesting way of doing it because you are capable of modeling interfaces between solid bodies. These brackets here, they technically have a contact surface which is separating, so it's surface to surface contact being modeled, and these welds are very easy to draw in a package like Invenor or SolidWorks, and it's one way to look at it. You can say you have more advanced simulation packages out there, but in those you have some restrictions or inconvenient interface for modeling in 3D. Things like Inventor and SolidWorks and some other software packages are built up from the other side of things. They are basically 3D drawing tools which have been extended to have 3D simulation extensions. So in this case, it makes it very convenient to keep modifying the geometry until your fast simulation results begin to match your design criterion. And that's pretty much the reason why I choose to stay with this instead of going into more advanced, less iteration-friendly environments. Yeah. So I just thought this is an interesting example. I want to share it because it shows some very, very fancy modes of failure where you can have a pull through, you could have a failure in tension. There are some contact points with high stresses near them, so potential slip of a leg out, and a small corner of a weld with a concentrated load, which is probably okay. The welds could be made a little bigger, and this is just the minimum size that I've looked for. And with all of these deformations and advanced simulation mode in NAstran expansion package, you can even see the residual stresses. And that also gives you an idea of how different the plasticity and elastic predictions are. The elastic prediction says that this part can hold approximately half of the load at 50%. That's where the limits begin to get triggered, and that would not pass. If you have a plastic simulation, the stresses redistribute, and you can find that the failure, the actual structural failure, happens around twice the load. But then that produces residual stresses. So if you have a different loading condition, you have to consider adding up these residual stresses from different loading directions if you're going to work in a plastic range. And also in plastic range, if anything is happening within the plastic range, that's a recipe for cyclic loading sensitivity. So frequency stress limits of cyclic stress limits, they should be checked on that as well. But if you did a simple linear elastic simulation and you stay below 260 in this case for S355, then you know that you are within the endurance limits of the metal, and it will technically never fail as long as the loads don't exceed the design limits. So it's very easy to make a component strong enough for a certain load. The elastic simulations are completely, fully enough. You just avoid concentrations of stresses and maybe refine the elements in those areas, and that's it. But you end up with pretty much half of the total holding capacity, which is of course safe, but perhaps not always the most efficient. Then if you have something that needs to hold the load only once, or twice or a few hundred times in exactly the same direction. Plastic strength with a coefficient reducing the strength could be an option. And if there's cyclic loads on this, then you have to make sure that they're not that many. And if there's changes in loading direction, you have to account for residual stresses and how they add up through different loading scenarios. And all of that can be done with Invenor NAstran.